If you've ever hung anything by a spring and just let it come to rest and then pull it down even further and let it go, you'll notice that the object just bounces up and down. All right, it just bounces up and down. What we're going to do in this video is give you the mathematical introduction to describe that particular motion. Okay, and this is known as Hooke's law, and Hooke's law applies to things like springs, rubber bands, things that are elastic that you can stretch, right? And the whole idea here is that as I stretch a spring, right, if I have a hanging mass on a spring and I pull it down beyond its natural resting state or its equilibrium position and I let it go, what happens is that the spring is exerting an upward force on the object and then trying to pull it up to the equilibrium position. But it has too much kinetic energy to stop, so it moves upward, and then it gets pushed back down. And then it gets pushed back up and down and up and down, and that cycle continues, if the spring is ideal, indefinitely. Okay, so how do we describe that particular motion? Well, we can't use the kinematic equations that we used in the first few chapters, because now we don't have a uniform acceleration. The acceleration is not uniform, and thus the force is not a constant force. If you remember the kinematic equations, we assumed that the acceleration was constant. When something is falling toward the surface of the Earth, the acceleration is more or less constant. So we could use those kinematic equations. Here we can't, because the acceleration isn't constant. So let's start to describe how we can describe the force and then how to describe the motion from that force. So Hooke's law states that the force on an object, okay, something like a spring, if I have a mass hanging from a spring, then the force on the mass from the spring is going to be equal to a negative sign, and that's important, I'll tell you why in a moment, times the displacement of the object. Okay, so for instance, if I have a spring and a hanging mass, right, so let me grab a spring and a hanging mass. So I'm going to let my system come to equilibrium, right? So it's just going to hang here. And this is the equilibrium position. If I pull the mass down even further, then it's that extra distance that I've stretched it, okay? That little extra distance that I've stretched it, that represents x. So if this is the equilibrium position and I pull it down here, then x is the distance from equilibrium to the position that I pull it down, okay? And you'll notice that it just bounces up and down, okay? So x is the distance from equilibrium position, all right? Now, what is K? Okay, K is what's known as the spring constant. Okay? K is known as the spring constant, and the spring constant has units of newtons per meter. All right, as you can see, if I need newtons on this side, then newtons must be on this side. Well, this is in meters, so this must be in newtons per meter, so the meters cancel out and I'm left with newtons. Now, the negative sign here implies that the force is always directed toward the equilibrium position. So as my object is moving upward, it's trying to move toward the equilibrium position, but it has too much kinetic energy, so it passes through and moves upward. And then, as soon as it moves through the equilibrium position, the force is now directed downward. And so since the force is directed downward, the acceleration slows and then reverses direction, and it pushes the object back toward equilibrium until it passes through. And then it's trying to pull it upward, so it slows, and it oscillates. So the negative sign simply means that the object doesn't continue accelerating off in one direction. Okay? The negative sign implies the object is being accelerated toward the equilibrium position at all times. Okay? Now, how can we find mathematically what the function x should look like? Okay? And what we want to do is look at the quote-unquote equation of motion. Now, the equation of motion simply is the description of acceleration. In theory, if I have any acceleration function, then I can integrate it twice and I can get position. Okay? So the equation of motion would look like this. F is ma, and if I just have a mass hanging off of a spring, then my mass is constant. So I'm going to have ma equals negative kx, and a is going to be therefore negative k over ma. And this is going to be the second derivative of x with respect to time. And so there's our equation of motion. The second derivative is proportional to negative of itself. The second derivative of x, whoops, this should be x. The second derivative of x is going to be proportional to itself with this negative sign, and the constant of proportionality is the spring constant divided by the mass. Okay? So how do we solve this particular equation? Well, you can do it one of a few different ways. But this is a second order differential equation, and if you've taken differential equations, then you know one of the best methods with which to solve a differential equation is to make an initial guess and to see how close your function comes and then try and adjust it, as opposed to maybe trying and integrating something that may or may not actually have a truly integrable function, right? The answer may not be analytic, in other words. Now this, you can integrate it, but it's actually a bit of a hassle to do it. What we want to do is maybe try and be a little more clever, okay? So the question is, what function, if I differentiate it twice, gives itself back with a negative sign, okay? If I have a function and I differentiate it twice, it will give me back that original function with a negative sign and then with a multiplicative constant out front. We're not too worried about that. What functions give themselves back? Okay? Well, you may say e to the x gives itself back. And that's true. E to the x, the derivative of e to the x is just e to the x. And e to the x, if I take the second derivative, it's just e to the x. So that gives itself back, but it doesn't have this negative sign. And you may say, okay, well, how about e to the negative x? And the first derivative is negative e to the negative x, but then the second derivative, I get that extra negative sign down and it cancels out, and it's just e to the negative x. So I don't get my negative sign out front. So then you might think, well, what about e to the ix? Okay, if you're familiar with imaginary numbers. But e to the ix is really just another way to write sines and cosines. Okay, so if you recall from your first semester of calculus, if I take the derivative of sine, then I get cosine. And if I take the derivative of cosine, then I get negative sine. So the derivative, second derivative of sine gives itself back with that negative sign out front. Same thing with cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. So I get my function back with the negative sign and some multiplicative constant if I have a multiplicative constant multiplied by x inside the cosine function. And we will use the cosine function instead of sine, because if I pull something down and let it go, then it's going to start from a point of maximum displacement, and that's where the cosine function starts. So we'll prove that the solution to this equation, right, the solution to this equation okay, we'll prove that the solution to that equation is something of the form like this. Okay, where this w is actually an omega, all right? It's omega, and we'll show you how it comes about. But what I want to do is differentiate this twice and show you that I get this, all right? So if I differentiate this, oops, this shouldn't be negative. If I differentiate this, it should be positive, all right? So if I differentiate this, I'm going to get a negative sign and if I differentiate it again, I get my function back with my multiplicative constant. So a cosine omega t is equal to x. So a cosine a cosine omega t is equal to x. So I get x back with the multiplicative constant, and this multiplicative constant, the square of it, all right, omega itself we call the angular frequency, and that is correlated with k over m. So omega squared equals k over m. Now we haven't defined frequency, period, or angular frequency yet, but those definitions will come in the next video. Well, the point of this was to show that if I have a cosinusoidal function and I differentiate it twice, then I get my original function back with the negative sign and the multiplicative constant, and therefore it's a solution of Hooke's law. All right. So the motion is going to be sinusoidal or cosinusoidal, depending on your situation and what initial conditions you take.